Good morning, Jackson. How you doing?
Good. How are you?
All right.
Jackson's gonna be a little late. Only because when he got out of the shower, his cat sat on his lap and he felt bad for moving her.
That's really not an excuse. There's certain things I don't share.
This is quite a bit thicker than the other lab.
Well, it's single-sided,
Okay.
but it is also quite thicker than the other lab.
Yeah.
Which I keep questioning my sanity, but it's like, you guys didn't come to school to watch me just lecture.
Yeah.
So we're gonna do labs.
Mhm.
That's what I keep telling myself. Plus, it's more fun for me too. I don't know. How many meters are in a mile? Where is everybody?
Yes. Oh, I don't. Yeah.
With this one, Eva?
I noticed that.
With this, Mr. Who? Does he keep the full 60 minutes?
Yeah.
Yeah.
What's up, Mr. Krause?
Not a whole lot. See, that's the tough thing. It's like, you know, I get it. You know, I want to get through all the material too, but like, you have 4 AP classes, right? I know like Kira does. To go all day, 4 classes.
She only has 3 AP classes.
Well, maybe I'm wrong, but I know a couple
She
people.
has 1 regular class,
Well, either way, to go 4 straight like that, that's kind of tough. Just pay attention.
but my day ends up much. So I can do that.
Well, in that case, I'm going to give you a lot of homework. All right. Oh, it's 10:01. I'm sorry. I'm talking about sports here. Sorry. I am the host. Can you all hear me at home?
Yeah, good.
Okay, that's always good because sometimes I forget to unmute and then I'm halfway through the lesson. So here's the plan. So tomorrow we're gonna start the lab. And Tuesday we're gonna finish the lab, okay? For those of you who aren't doing the lab tomorrow, so you wild people and you remote learners, you guys are gonna be watching a lecture that goes through the homework and starts the next chapter. And then over the weekend, you guys are gonna have a take-home chapter 13 test. And then on Tuesday, then the cat people will watch the lectures, okay? So everybody's gonna have the take-home test over the weekend. So you got Friday, Saturday, Sunday, and Monday to do the take-home test. There's no way to fit it in class like I wanted to if we're gonna do the lab. So as we go through the lab, you'll see that it's quite involved. But that's the reason why we're doing it completely in class. So we'll get the data in class, we'll do all the calculations in class. The only thing you're gonna have to do is the summary on your own. So, and bring your iPads to class because we'll graph on the iPads and hopefully we'll be able to print from the iPads. If not, you can always email it to me and then I can print your graph, okay? So, any questions at home about the plan before we, yep, Nathan Jern's got a question.
I don't think I'm gonna be here tomorrow.
Okay, Nathan's not gonna be here tomorrow. That's, so, well, that's unfortunate for you. But you're just gonna get the data from somebody, so. Any other questions? All right, let me share my screen. And then we're gonna walk our way through this lab. I can give you a printout if you want. Otherwise, you'd be printing it off at home or just writing your answers on a separate sheet of paper. But if you get, do you want, does anybody want to print a copy right now? So I know.
Yeah, I'm good.
Okay, so I can print, but you're not gonna be here tomorrow. Unless you stop back later today, I could give you a printed copy. Okay. Oops. I gotta go to Canvas. So you're gonna want to take notes on this lab. All right, so I know you haven't had a chance to read through this, so we're gonna kind of read through this together. And maybe you want to highlight or underline important sentences, okay? So in this experiment, we're gonna study the kinetics of a reaction. This reaction is called a clock reaction. And we want to determine the rate of the oxidation of iodide by bromate. So this is our reaction. And we want to find the rate of the reaction, okay? So as you know, you can find the rate expression down here. So we take the iodine, raise it to the nth power. That didn't come out quite right. Those are exponents. The bromate to the mth power and the H plus to the P power. we're going to try to find N, M, and P, okay, in the lab. We're also going to try to find K, all right? Now, when we did the homework, all that data was provided for you, right? In chapter 12, they would tell you the concentrations and the rates, and then you would do, oh, experiment 1 over experiment 2, and then you have things cancel, and then you'd solve, okay? Well, you're going to actually do it this time, all right? So how are you going to measure the rate, all right? So the integrated rate law, we could say that we're going to measure the change in rate of bromate over time. So we can measure how the concentration of bromate changes. Or we can measure how the concentration of the iodine changes. Now, I know it's only been one chapter, but what's the relationship between the iodine and the bromate as far as the rates go? You have to divide that one by 6. Or we could measure the change in rate of the H plus over time. And there's a 6 there. They're all going to be the same rate. So the question was, will all of those give the same rate? Yes, as long as you divide by that 6, you'll get the same rate, all right? So we're getting the iodine from potassium iodide, okay? So that's where we're getting our iodide from, is from potassium iodide. We're getting our bromate from potassium bromate, okay? And we're getting our H plus from HCl. So that's where we're getting those 3 chemicals from: potassium iodide, potassium bromate, and hydrochloric acid. So now my question is, how can you measure the concentration change of something? All 3 of those solutions are clear: potassium iodide, potassium bromate, and hydrochloric acid. They're all clear solutions. So when you mix them together, you're not going to see anything. You're not going to see the reaction occurring. So how can you tell that there's any change going on? Well, that's where we're going to have 2 other reactions occurring that do change color and will allow you to see what's going on. So I am going to just jump down to the bottom where I can get some space to write, okay? So I'm going to rewrite that equation. And we said that the rate could be the change in concentration of the bromate over time, or it could be the change in concentration of the iodide over time divided by 6, or it could be the change in concentration of H plus over time divided by 6. But those aren't our only 3 options. So it's not just that the concentration changes for the reactants, the concentration can change for the products as well. So we could, these are all negative, reactants are decreasing, right? Products are increasing. So we could measure the rate based on the iodine, or we could measure the rate
of the bromine. Water, we could, but it's a liquid, so it's kind of hard to measure the concentration of a liquid. So all three of those are equal to the rate. So we could use any of these substances, any one of those six to measure the rate. How are we doing at home? Any questions so far? So we're going to have a second reaction occurring because the first reaction does not produce a color change. So like I said, if you're watching this reaction here, just going to call it reaction one. If you watch this reaction, you would see a whole lot of nothing. It would just be clear. So what we're going to do is we're going to have a second reaction occurring. And that is the iodine is going to react with thiosulfate. And the thiosulfate is going to produce iodide ions and S4O6. And that's reaction two on, you can see on page one. So what's going to happen is we've got our reactants. What's going to happen to the concentration of the reactants, Avery, as the reaction proceeds? So we've got our reactants right here. What's going to happen to their concentration as the reaction proceeds? Go ahead and unmute yourself, Avery, and tell us what you think. Avery, are you there?
Yeah,
What's going to happen to the concentration of the reactants?
it's gonna go down.
They're going to go down. So the concentration of the reactants are going to go down. What's going to happen to the concentration of the products, Ari? Ari, are you? Oh, yep. Oh. So what we're going to do with this second reaction is as the products are formed, the iodine is going to immediately react with the thiosulfate. Okay. So the iodine that's produced will immediately react with the thiosulfate and produce this. Okay. Yep, Ava.
Can you read what's in that first parenthesis of reaction two?
The first parenthesis is S2O3. Okay, and that's on the front page of your lab too. Now, what's going to happen when the thiosulfate runs out? When there's no more thiosulfate, the iodine won't have anything to react with. Okay, so when all the thiosulfate is gone, then the iodine will run out. I mean, when all this runs out, then nothing is there to react with the iodine, okay? That's when the third reaction occurs. The iodine is going to react with the starch and turn blue. So the iodine will react with starch and turn blue. We can call it reaction 3. So now we've got a color change, something you can see. Oh, I forgot the 2 out in front here. 2 there, sorry. So the rate of reaction 2 is going to be this. So that's for reaction 2. Oh yeah, sorry, I forgot the negative in front of the thiosulfate. Jackson was very nice to point out my mistake. So in our lab, I'm going to scroll up. Or do you need more time writing that down? You get it, Deering? So this is our twisted logic. We know the concentration of the thiosulfate. Okay? We know the concentration of the thiosulfate, right? It's well, I won't spoil it for you, but we know the concentration of the thiosulfate. So what's going to happen when the concentration of thiosulfate gets to 0? What's going to happen when the concentration of thiosulfate is 0? Let's go back and look at our equation. When this runs out, the iodine is going to react with the starch, and what's going to happen? It's going to turn blue. So you're going to start your stopwatch. You're going to start your reaction, you start the stopwatch. When the solution turns blue, you know that all the thiosulfate has been used up. So you can figure out the rate based on the change in concentration divided by the change in time of the thiosulfate, okay? But we don't care about reaction 2. We want to know reaction 1. Well, this is where the fun part comes in, okay? And hopefully I can do my math right. I should have. So if this equals this, all right, I am going to substitute this in for different color. This, okay? Substitutive property. I got the change in iodine divided by T. So I'm going to substitute this just in for that portion. So when I go back up here, I'm substituting in the change in thiosulfate. What's 3 times 2? 6. All right, Deering, this is the advanced class. So in other words, the rate for reaction 1, the rate of reaction 1, and I'm going to just go down here. Will be equal to the change in concentration of the thiosulfate divided by 6 divided by time. Okay. So that's how we're going to find the reaction. The rate of the reaction is by seeing the measure and the change in the concentration of the thiosulfate. Okay. So any questions at home before we show you some lab technique? All right, so normally what we would do is have groups of 2, and you would perform all 8 experiments, okay? That, with 2 people working together, it takes time, and we're rushed with 2 people working together. So how is one person going to do it by themselves? We're not. We're going to divvy this up, and we're going to compile class data. So like tomorrow, I'm going to give, I might as well assign you right now. Jackson, you're going to do reactions, experiments 1 through 3. Okay. Ava, you're going to do 2 through 4. Deering, you're going to do 3 through 5. Jurens, you're going to do, just kidding, Jurens won't be here tomorrow. So Lucia, if she shows, you're going to do 4 through 7. Okay. And then the wild people on Tuesday are going to do the other ones. So we're going to have at least 2, maybe 3 people doing each experiment so that we can average them just in case, God forbid, I know this wouldn't happen during, but if you messed up,
Oh, wow, mess up.
there'll be someone else doing reaction number 1 so that if you mess up, we don't have to, fret and worry and cry. So all of these are at room temp. Then we're going to see what happens to the reaction when we change the temperature. That's part 2. Okay. So we can already guess what's going to happen to the reaction. It's going to speed up. Okay. So the solutions should turn blue within 5 minutes. Some will turn blue very quickly, especially when we increase the temperature. So we're going to do 4 temperatures, 40, 20, 10, and 0. So let's see here. Tomorrow, Jackson, why don't you do 40%? 40%, 40 Celsius. That'll be the hot bath. Ava, you've got 20 or 10 degrees Celsius. Okay, you got 10. Deering, you're going to do 0. And then Lucia, you're going to do 40 degrees. Okay, if you're here tomorrow. We don't have to do 20 because 20 is room temperature. We'll have already done that. All right. All right, so Ava's going to film me over here while I show you how these things work.
Wait, which one is that?
Okay, so tomorrow you'll have to do, there are 6 things. We've got the potassium iodide, the potassium bromate, the hydrochloric acid, the water, the starch, and the potassium bromate, I think is the last one on the table, right? KBROA03. Okay, potassium bromate. So I'm just using food coloring here so that you can see it at home, but all your solutions are going to be clear. This is a pipette bulb, okay? So you squeeze it and it creates a suction. You put in your pipette tip and then you just, there's a little button here, I'm sorry, a little lever that you can suck up or expel. So I'm just going to put it in here. Oh, this is why we're doing this. So we learn technique. So you squeeze the bulb outside of your solution, because what happens, and I'll just show you because this is not dangerous. What happens if I squeeze my bulb in the solution? Oh, it didn't happen. You can, oh, I got a crappy one. It's going to make bubbles. So if I do this, oh, didn't do it again, but that's okay. What can happen is if you squeeze in the solution, it can bubble over, okay? So that's why I always squeeze it outside. And then you start just pulling up the lever, and you want to get it to 0 because it will make your stuff easier, okay? Now, the first thing we add is, what's the first thing we add on that table? The iodide, and then comes the
Water.
the water,
Yeah, then the water.
and then the hydrochloric acid. Okay, so you want 1 pipette for the iodide, water, acid, and the thiosulfate. You want another pipette for the starch and another pipette for the potassium bromate. So the potassium bromate, maybe put a star on there, should have its own pipette.
Come here and start mine.
And the starch should have its own pipette. Okay, so you should have 3 pipettes and all of them laid out. But you have only 1 for the starch, only 1 for the potassium bromate, and then the other pipette tip can be used for everything else.
Girl, what are you doing?
So you'll have tape to label your pipette tips so you don't get them confused, okay? You get a little bit of sample, what you need from the big beakers that I have. Never, ever, if you have too much, go back and pour it into the stuff that you got it from, because you'll contaminate it for everybody, okay? So, and that's in any situation. If you have too much, just dump it down the sink at the end of the lab, okay? Don't go back and dump it back in. So to speed things up, you take your potassium iodide. You don't want to do just the first one and then say, okay, now I need to get water, okay? Because first of all, you're going to waste solutions and you're going to waste time going back and forth to get your stuff. So when you pipette, squeeze, then suck up. So I need 2 milliliters, 6 milliliters, 4 milliliters. So I do my 2, then I go to the next one. I do 4, I go to the next one, and I do. So if you do 1 at a time and you label your test tubes, it goes a lot faster because you're not having to switch. Now, what if you need to get the little bit out at the end? Okay, so I wanted to add 6 mils. There's a little bit left in the end. There's a button there. That button is to blow air out the tip, okay? So what we say is you blow out the tip, press the button, and it pushes out the little last bit, okay? So again, that's technique. Then you go back and you can suck some more up. Now you want to pay attention to what you're doing. You don't want to suck solution up into the bulb. Because if you suck acid up into the bulb, it's going to wreck the bulb, okay? So make sure you don't suck stuff up in there. If you suck up too much, uh-oh, I got too much. I went past my 0. If you suck up too much, then just dispense it back into your thing, okay? Because it's a lot easier if you start at 0, because if I need 2 mils and I start at 0, I just go down to the 2 mil mark, right? So it's always easier if you start at 0.
I need 2 mils.
So your homework is to read through the directions. I'm going to tell you the directions, but you still should read them. You add everything you need, get all your test tubes ready, and then the last thing you add is your potassium bromate, okay? Now that one,
Oh, man.
got some water here, just a- So for the potassium bromate, that's when you're going to start your stopwatch, okay? So it says, the way I would do it is, and I'll remind you, have your cell phone out, have your timer ready, have the stopwatch ready, start it, and then dispense your milliliter, okay? And then do a quick inversion
Oh, Jesus.
and watch it turn from clear to blue.
Wait, is this a dumb question if I ask if it's gonna burn your thumb?
It's not gonna burn your thumb. It's not a dumb question to ask. All the stuff in there is very weak, and nothing is toxic. So dispense your 1 milliliter of potassium bromate, quick invert, and that, but you want, like I said, you want to start your stopwatch first, dispense, invert, and some of these will take about 40 seconds. Some of them are going to take 5 minutes, okay? So this is where it will be interesting because as you can tell, consistency is going to be hard because you want to stop it when it turns this shade of blue. So you stop your stopwatch when your clear solution turns blue. So
Not when it starts to turn like slightly blue.
not when it's turned slightly blue, this shade of blue. So that's where it's going to be difficult because it will continue to get darker and darker and darker and darker until it's like indigo, or almost like a dark, like Nathan's hat blue.
Oh,
So
I'm doing a city job with this.
that's where we're going to do the averages. And hopefully if we take the averages, it'll be okay because everybody is going to be subjective in a sense when they're stopping their stopwatch because you're just looking at it and making a subjective call as to, oh, I think it's starting to turn blue or it's starting to turn this shade of blue. Okay.
Blue Jolly Rancher blue.
Similarly,
You're welcome.
when you are doing it at a different temperature, so why don't you just, here's the hot plate over here, or the water bath. You want to get your test tube all set,
There should be a movie
get everything
producer.
all set.
Oh, God.
So you have your test tube in there, then you add, well, start the timer, then you add, okay? So when you're doing it at the different temperature, you want to have it in the ice bath or the water bath before you start. Okay? Thank you, Ava.
You're welcome. Hey, cutie. Hi, Kira. Wait, am I done?
You're done.
Oh, period.
Thank you.
Bye.
No gang symbols. So hopefully you're able to see that fairly well. And again, that's the idea is you need to learn how to pipette correctly. I use the pipette bulbs. So that's one of the reasons why we're doing this lab. Okay. it's gonna take up, our calculations are gonna take up 2 days. I mean, here, the pre-lab is taking 1 day, the lab will take a day, going through the calculations will take 2 days. We got 4 weeks left of class. Yeah, it's impossible for us to get through chapters 14, 15, 16, 17 in 4 weeks. So I knew that going into it. All my lectures are on there. If you want to keep, I've got all the lectures from 14, 15, 16, 17, 18 pre-recorded. So you can always, if you want to, watch all the info from those chapters. But I really want to make sure we do labs and go at a pace where you're actually going to remember what I taught you. So it is what it is. We'll see what happens during quarter 4. I'm all in for summer school. Deering said he's in. So, all right, any questions before we start going through the homework? All right, let's,
Why doesn't it start the iodine reactor to start right away? To start
okay, so that's a good question. It says, why doesn't it start reacting right away? Okay, so got to go back to notability. I left my little thing over there. All right, so you have to have, Jackson asked, why doesn't it start turning blue right away? You have to have iodine to react with the starch, okay? There is no iodine. Why? Because all of the iodine is reacting with the thiosulfate. So therefore there's literally no iodine to react with the starch. Once all of this is used up, then the iodine is free to react with the starch and turn blue. Okay. I am going to make a video of the problems. Okay, so you can watch the video of the answers to the homework problems, because I would like us to start doing. Well, we'll go through a couple problems from the homework, and then we're going to start our calculations for the lab. Okay. Didn't I thought I put a problem set up there. Maybe I didn't. If I didn't, lucky for you, then you get another day. I guess I didn't. Okay. The problem that I really want to make sure we go through together is number number 67. Okay. 67. Sometimes people get confused with the difference between rates and equilibrium. So it's kind of good that we're doing the kinetic lab, because that way you'll help keep it straight in your head, or it'll confuse everything, one of the two. All right, so what's going to happen for each of the following stresses? So I haven't referred to it by name, but Le Chatelier's principle, and I don't know how to spell it because it's French. Le Chatelier's principle means that a reaction will shift in the direction that reduces the stress. Okay, so reaction shifts to counteract or reduce the stress, whatever the stress to the system was. Human beings are kind of like this too, right? AP chemistry is too stressful, so you skip class. You shift to in order to reduce the stress. You guys don't do that. Well, in the short term. All right, so what's going to happen? What's going to happen if we add, well, let's write our equilibrium expression. We'll usually need that at some point. Okay, so for letter A, what's going to happen if we add hydrogen? Which direction is the reaction going to shift?
Right. No.
Well, that's where we should use towards products or towards reactants. So if we add this, it's going to shift us towards the reactants. Okay, because essentially we have too much product then. So we have too much product, it's going to shift towards the reactant side to get rid of the extra product. And if for some reason you do decide to take the AP test, there's always questions like this on there. What if we remove iodine? Hard to write on this thing. So if the amount of iodine is decreasing, no, you're right. I just got to give wait time. So if we're removing iodine, that means the concentration of iodine decreases. So we have too few products, so we're going to shift towards products. See, HI is removed. So if we're removing high, that means we need to make more of it, so we shift towards the reactants. Now the one that gets people are the next three. The first three make you feel good about yourself. And the next three are to make you not feel good about yourself. No, I'm just kidding. In a rigid container, argon is added. Okay, so where is argon in the reaction? So argon is not there. So adding argon will do nothing. Okay. And this is maybe where people go think about this, and the thinking is flawed. They're thinking that, okay, I added argon. What's going to happen to the pressure in the container if I add argon? The pressure is going to go up. And so sometimes people think, okay, the pressure is going up, so I want to reduce the pressure, because that's what Le Chatelier's principle says. If I add something, it's going to cause the shift. Well, this is going to, it will increase the pressure in the container. However, it won't change the partial pressures of these. It doesn't change the partial pressures. And what goes into the KP equation? The partial pressures. So that's why argon, adding argon doesn't do anything, because it doesn't change the pressures. Whereas adding these gases, adding hydrogen gas, adding iodine gas, that's going to affect the reaction. Okay, but adding argon won't do anything. Now, if I added something like oxygen, well, that would be a problem, because guess what? The hydrogen's going to react with the oxygen. and therefore it's going to drive down the concentration of oxygen. I mean, drive down the concentration of hydrogen, and therefore it would affect your reaction. That's why they picked argon, because argon is a noble gas. It's not going to react. Okay. Adding something that reacts is more of a chapter 14 and a chapter 15 question. In this chapter, they picked argon because it doesn't react. E, the volume of the container is doubled. Okay. So now what's going to happen to the pressure? Pressure is going to go down, right? So Le Chatelier's principle says, well, if the pressure is going down, we need to counteract that stress. Oh, this problem. Okay, this is unfortunate. So let's just pretend for a moment that this is a 1. Okay, we're pretending. How many moles of gas do I have on the right side now if I'm pretending? 2 moles to 1 mole. If my pressure was decreasing, by shifting right, I could increase my pressure because I would be creating more moles of gas. So you have to look at how many moles of gas there are, reactants versus products. So because I would be creating 2 moles, I would actually be shifting right. But in the real problem, how many moles of gas do we have on each side? 2 moles and 2 moles. So if I shift to the right, do I increase the number of gas particles? Nope. If I shift left, do I increase the number of gas particles? Nope. So in this case, changing the volume will have no effect. However, in most circumstances, you change the volume, it will change the pressure, and the reaction will change.
So changing the volume of the whole thing doesn't change the partial pressures of the.
In this scenario, if we had this, where did it go? If we had this, oh, I've done something. No, I don't want to write. How do I get away from that? Yeah. So if I had this reaction, 3 hydrogen gas plus nitrogen gas producing ammonia gas. If I doubled the volume, which direction would this thing shift if I doubled the volume? So if the pressure is going down, I need to increase the pressure so it would shift towards the reactants, because now I'm making 4 moles of gas. Okay. So when I doubled the volume, it affected the pressure and therefore I shifted. Okay. Letter F, the temperature is decreased. All right. So temperature affects the K value. All right. It says the reaction is exothermic. Reaction. Yep. Okay. Exothermic means the products are lower in energy than the reactants. All right. So the reactants have to overcome this activation energy hill. The products have to overcome this activation energy hill. So I'm going to draw a couple diagrams here for you. This is energy. Nope. This is energy, kinetic energy. This is number of molecules. So you always have a what's called a Boltzmann distribution or a bell-shaped curve or a normal curve. Hey, you just got done with stats. You know all about this. Given any grouping, you will always have some on the very high end with a lot of kinetic energy and some on the very low end. The formula for kinetic energy is 1/2 mv squared. So for my hydrogen iodide, I'm going to have some molecules with a lot of kinetic energy. All the molecules that are above that value will have enough energy to react. Okay. So there's the activation energy. All the molecules that are above that will have enough energy to react. If we do it for our products, the distribution looks the same. This is for hydrogen and iodine. But the activation energy for the reverse reaction is much higher. Therefore, there are fewer molecules that could actually react. So there's a higher hill for your products to get over than your reactants. If I increase the temperature, it shifts the distribution. So if I increase temperature, it shifts the distribution over. Okay. Who am I helping more by increasing the temperature? And I kind of put it this way. Suppose Jerns and I are going to race up a hill. Okay. Now I'm out of shape and Nathan is a young guy. So who's going to get up the hill first? Nathan, right? So now we're going to increase the temperature. And by increasing the temperature, what I mean is Nathan's going to get a car and I'm going to get a car. Now we're going to race up the hill. Who is it helping more, Nathan or me? Me, right? So similarly, by increasing the temperature, I'm disproportionately helping the products in this case. It's exothermic. You're helping the one who's got the higher hill, the bigger problem to overcome. So in this case, by increasing the temperature, I'm going to help the products get over the hill. We're going to shift towards the reactants. So it speeds up the reaction and remember, it changes the K value. So it's changing the K value because it's helping more products get over the hill disproportionately. The reactants, they can already get over the hill. It's a small hill. They can already get over it, no problem. These guys, that's a big hill. So by increasing the temperature, I help more of those get over their hill. So that's why increasing the temperature does that. All right.
It's drawing a line like halfway through the hill from way smaller and the hill on the left doesn't change.
Sure. All right. We get out at 11, right? Yeah. Some things haven't changed. Everybody's packing up here. Okay, let's see. We didn't have number 20 to do. Okay, so tomorrow you're gonna watch the video on how to do the rest of the problems and a video that's gonna introduce the next chapter. And those who are cats are gonna do the lab, and then we'll flip flop, and everybody will have a take home test. So for your homework tonight, you're gonna do your pre-lab. So remember the title, the purpose, and the procedure. Now, if you want to literally cut and paste the procedure, that's up to you. Otherwise, summarizing the procedure is what we're expecting you to do, is to like read through the procedure, summarize it into a paragraph. But if you just want to cut and paste it, that's totally up to you. Do you guys have any questions? The homework from last night, I'll create a link for you guys to submit it by midnight tonight. So hopefully your homework is already done. If not, you'll have till midnight tonight to submit it. Any other questions? Lucy, are you coming to class tomorrow? Because I need to know how many lab stations to set up.
Yeah, I am.
Okay. All right, well, you guys have a good day, and I will see you tomorrow.
We put the half pressure thing. So it says it relates to like the one law, because if it's there, you have a half. But since this is just the number of moles, so also you have a 4 and 4. And if you change to 3, then also you have a 6 in the bottom, and that's why it.
Yeah.
Okay. Just trying to relate the intuition.
Come on now, y'all.
See you later.